Right, so lecture number 16. So there was a question on corner points. How do we deal with that? Because the meaning of corner points is that you have two boundaries meeting there. So which boundary condition should I be applying? That is a confusion. So there is no answer to that. I mean, there is no thumb rule. You apply whichever one you want. Now with experience, we realize that sometimes applying a different boundary condition can have an effect, so that if things are not going well, then you try to change the boundary which the corner point is sharing with itself. But usually what we do is we tend to apply the lower order boundary conditions. If you have Dirichlet on a boundary, then you tend to give that condition to the boundary, to the corner point, rather than giving it a Neumann which is coming from another boundary. Okay, so there is no thumb rule, just no rule. So all I can say is you apply the lower order boundary condition. Okay, the next practical aspect that I'll want to discuss, although we implemented that in the lab, is on the stopping criteria. So we said that we have used the L2 norm in this case. Okay, so rather than talking about the difference, we talk about the relative difference.
If we apply lower boundary condition, then transition has to lower.
But not lower order in the sense of discretization, lower order in the sense of derivative. So if you have a Dirichlet and a Neumann, you go for Dirichlet. That's what I mean. So stopping criteria for iteration. So if you are applying the L2 norm, rather than using the error, we tend to use the relative error. So we say theta nu ij minus theta old ij, and then you divide that by theta old ij, so that gives you the epsilon relative. And you can use this to calculate your RMS value, the L2 norm. So that is much better when using it for comparing with the tolerance than using the difference of nu and old. And the reason being because see the theta values can have different orders in the domain. It can be 10 somewhere and let's say 100 or 1000 somewhere. 1001 will have a difference of which is much larger than typically, which is of the order of 10. So what happens is the error tends to be dominated by the regions where your theta values are larger. But that is not all we want is accuracy. So we want that the accuracy in terms of the relative difference should be small everywhere. So when we are adding things together, then we can tend to get dominated by the higher orders if you are using absolute errors. Right, so for the iterative schemes we use Gauss-Seidel rather than Jacobi. So Gauss-Seidel converges much faster, typically twice as fast as Jacobi. And then we said that we can also use successive over relaxation with an omega, and we saw that with omega you can get up to 30 times faster convergence. So we are optimizing things now. So Gauss-Seidel successive over relaxation. Is there anything we can do further to improve things? The answer is yes. The first thing is if you think in terms of how you programmed, how you write, how we wrote the loops. So for the problem that was given in the lab, it was a Dirichlet boundary condition on all boundaries. So we were only updating the interior points. So for the interior points, we start with this point, the bottom left. Okay, that's the first point, first row that is not known. Then we go to this one, then we go to this one, then we go to this one, and so on. So we are moving in a certain way. We move like this, then we move like this, then we move like this, and so on. Okay, so we visit the points left to right, bottom to top. Okay, and that is the reason we said that when writing the scheme, which includes contribution from these points in Gauss-Seidel, what we can do is when we are calculating the value for this point, this and this is already known. So we use the new values here, and these values are not known. The I plus 1 and j plus 1 are not known, so we use the old values here. And so this whole reasoning is because we are moving left to right, bottom to top. Now when we move in a certain direction, what happens is the errors tend to propagate. So let's say there was an error at the first point, it tends to propagate. So the errors tend to propagate from left to right, bottom. So the top rightmost point, let us say in this case maybe this one will have sort of the maximum error as compared to the one that we started with. So there is some sort of a bias in the error in the solution. So to remove the bias, what we do is, and since you know that you're doing multiple iterations, not just one, like we saw in the lab a couple of minutes ago that we ran around hundreds of iterations. So one iteration we go like this, and the next iteration we go in a different way. We start from the top right, start going like this, and then like this, then like this, and so on, to remove this bias. So first you sweep bottom left to right, bottom to top like this, and then you sort of, the next sweep is backwards. And it doesn't matter, I mean it's our choice. Ultimately we have to sweep all the points. But if you are sweeping from right to left, bottom to, top to bottom, like the sky blue that I've shown in the color, then you have to write your residual in a different way, because this time the old and new values are different. Okay, this time the left and the lower values are sort of the new values, and the top and the right values are sort of the old values. Okay, so this method where you change the sweep direction is called, it's still Gauss-Seidel, but we are it's called symmetric SOR. Is that clear? So this tends to increase the accuracy. Number of iterations will most probably still be the same or maybe different, because now since we are getting closer quicker, so we might reduce the number of iterations. Right, can we do any better? The answer is yes. So the next one I'll discuss is called schemes which are called block iterative schemes. So they're also known as implicit iterative schemes. It's interesting because it has implicit as well as iterative. Now we said that iterative schemes are used for implicit discretizations, but here what we'll do is we'll use both ideas together. We'll also use implicit scheme, which is to sort some sort of a matrix equation, as well as iterative. So that will help us improve this convergence or the number of iterations further. So this is going to be faster than Gauss-Seidel SOR that we have just discussed. So there are different types of scheme. We'll just discuss one, which is called SOR by lines. Okay. So the one we'll discuss is called Gauss-Seidel SLOR. So L stands for by lines. So this is called SOR by lines. So I'll tell you what it means. So if we look at the difference equation for our or the discretized equation that we had for the implicit scheme, so this looked something like we had theta I minus 1 comma j, then we had a term which had theta I comma j minus 1, then we had theta ij term, then theta I plus 1 comma j, and then theta I comma j plus 1. Okay, and they all had coefficients. There could be a right hand side coefficient as well, so we'll call it P. So in SOR, I mean Gauss-Seidel, what we are doing is we visit points in a certain direction, let's say left to right, bottom to top. So we go like this, and then we move to the top, and then we go to the next line, and then we go to the next line. So we visit each and every point. And whenever I visit a point, what I do is I am using values. So it has this kind of a stencil in the equation. So I use the left, right, bottom and top values to calculate the value at the I comma jth point for that theta. So this and this I do it for each and every point. Now if you think about it in the sense of how we are calculating the value of theta, it's like an explicit method, right? So to calculate the value at a given point, we are explicitly using values at other points. It just happens that the left and the bottom point values are updated, so we call them new values, and the top and right points, they are old values. But when you write the equation in a loop, you are sort of explicitly writing the value of theta at that I comma jth point in terms of points around it. Okay. What we can do, I mean, alternatively, is rather than writing, and the reason, and the whole reason we did this was because if we tried to use an implicit with an equation, we used to get a matrix which was banded. So we got a matrix which had 5 lines, 3 of them were close, but then there were 2 which were very far away. And that was the reason we could not invert the matrix, or we could not use the Gauss elimination method, because that results in a dense matrix when you are doing the calculations. So if somehow I can reduce that 5 bands to 3 bands, or a tridiagonal matrix, 3 lines, then I can use TDMA, tridiagonal matrix algorithm. And that is what we do here. Rather than using a completely iterative method, we sort of reduce the matrix to a TDMA, a tridiagonal matrix, and then we can apply the TDMA algorithm, because that is very efficient. So what I do is, rather than calculating point by point, I say that I pick this whole line and I'll be solving the whole line together, just one line, not the whole matrix of points, just one line. Okay, let's pick a line which is somewhere in the middle. So let's say we are solving for this line, which includes all these points. Now to calculate the value at a point, let's say this one, I have this kind of a stencil. Let's use a different color. So it uses this, and these 4 points. So what I do is, for the bottom and the top point, I will treat it as explicit. So I'll say that the bottom point already is calculated because it's coming from the previous line, and the top point I'll take the old value. But for the ij point I comma I minus 1 comma j and I plus 1 comma j, I'll solve them simultaneously. So what happens is this equation that we have here, we sort of reorganize this equation. So I keep theta I comma j term here. I have theta I minus 1 comma j term, and I have the I plus 1 comma j. So I'll let's, because we are calculating new values, so we call them new. So these are unknowns solved together, and on the right hand side we have theta I comma j minus 1. So for this I am using a new value, but this is not being solved with this, so we'll have to sort of, I'll put an e here in the sense that it's already known, so it's sort of explicitly given. And then we have a term which is theta I comma j plus 1, which is old value because it's still not being calculated. It's coming from the old iteration. So remember, this is still one sweep of Gauss-Seidel, except that rather than writing loop for each and every point in the line, you solve a tri-diagonal matrix for the whole set of points together. So now you see that you have an equation. This equation is for a particular point, so it requires a left and a right point. And now if I write the equations for all the points in that line, I get a system of equations and I can solve them together. So by solving that matrix system, where the unknowns are your unknowns which are starting from this point and going to this point, so they'll have indices which is let's say I equal to 1 and then some j value, then I equal to 2 comma j, and all the way to I equal to n minus 1 comma j. So these are the unknowns here, and you will see that you will get a tri-diagonal matrix because every equation has one point to the right and one point to the left. So that gives you a tri-diagonal matrix, and then you have some RHS value. So this is called Gauss-Seidel SOR by lines. We are still doing over relaxation because we are trying to get the optimum value. So we are trying to use, we are still using omega here, but we are visiting the points as lines rather than discrete points. So you sort of write sweep loops which are equal to the number of lines you have, and each line gets solved using a tri-diagonal matrix algorithm. Is that clear? Now what is the benefit? The benefit is the speed with which the boundary information gets diffused is much faster. Because think about it, ultimately this equation is simply diffusing the boundary value into the domain. There is nothing being generated right now. Although the equation could have more terms, but the way we have written it, because we are solving this particular kind called the parabolic equation, the heat conduction equation. So here what's happening is the boundary information is diffusing into the domain. The faster it happens, the better it is for us. So if you do point by point, what happens is, if you look at this, let's say a point here. So this point talks to this, and this. So it talks to the left point, so left boundary gets information here. And then you visit this point. So the left boundary moves here. But the right boundary information has not moved to the left. It's only the left boundary moving to the right information, the way we are visiting. But if you visit the whole thing by lines, the complete information travels to the whole line. Okay? So by visiting things by line, the boundary information gets percolated or transmitted into the domain much faster. And that is the reason you get a better convergence. And that is the reason if you have a higher order scheme, so a lower order scheme will have a fewer number of points. Higher order scheme will have more number of points. So more number of points talk to each other. If I had a third order scheme in this case, then I'll have two more points in the one more point in the x direction, one more in the y direction. So that means more talking is happening. So things will happen much faster. but then you have to have more computational work. So this is the reason that it converges much faster. But you might ask that, that is fine. I mean, it will converge much faster. But the point is, does it necessarily mean that see, we are reducing the number of iterations or the number of sweeps. But to solve the TDMA, we require some computational effort. It could happen that the computational effort required for solving the TDMA may be more, because ultimately we're talking about the number of floating point operations that the computer has to perform. So it could happen that the number of flops required for solving the TDMA could be same or even more than the number of points, number of flops required if you have to explicitly visit each and every point. It could be the case, but generally what happens is, because of this idea of things being transmitted much faster, you tend to have faster convergence in terms of computational times. Iterations definitely are lower, but overall time the computer takes will also be much lower in this case. Okay. Now these are I don't expect you to be using all these in your programs, but you should know about these, because when you see a commercial code or when you see an open source code, you'll have these options. Which one do you want to tick or click? So at least we should be able to understand what they mean. Only then we can sensibly decide whether we want to click them or not. But I mean, if you start doing things yourself, you'll think about, you start with simple cases, then you try to make them more optimum by going one step further. Okay. Right. Another method that we tend to use is a scheme called, or another scheme that's called ADI, coming from a similar idea. It's called alternating direction implicit. So here we don't even use iterative method. This is so we said that in successive overlapping with lines, we do a line and we use TDMA in a line, and then we do iterations, sweeps for all the lines. But here what we do is we sort of this is not an iterative method at all. So here what you do is you have a two-step approach. In step number 1, now remember the backward time center space. So we had theta n plus 1 minus theta n upon delta t, and this was you had discretization for x and y. So this was done at n plus 1th time, and this was also done at n plus 1th time. So that resulted in a backward time center space, but then that is where the whole problem started. So here what we do is step number 1, instead of going for the complete time step, we go for sort of half a time step, and we say that for this first half I'll write the x direction as implicit but the y direction as explicit. It's a very smart idea. So if you look at the step number 1, which is drawn here, now in this case, if you rearrange the equation, the only unknowns you have are in the x direction, right? It's like you start with a line like this and you solve it completely, because the y values, they are all at nth time, sort of explicit. So this line that you have, the blue line that I have shown, the horizontal line, you solve it all together using a TDMA, because the unknowns are, you have I minus 1 here, and you have a theta I plus 1 here, comma j, and then you have a theta ij here anyways. They're all at n plus half, so that is the unknown value here. Okay, so you have a TDMA that you can solve. and then you move up, you solve for the next line, again a TDMA. It's very similar to what we discussed, right? And in the next step, this time we go for theta plus half, n plus half to n plus 1. And the first part is at n plus half, and the second part is at n plus 1. Now n plus half is already calculated for all the points. So what happens is, it's as if you are solving a TDMA for vertical lines now, because the unknowns are theta n plus 1 ij, and you have I comma j minus 1 here, and you have I comma j plus 1, and you have an ij here, all at n plus 1. So the unknowns are in the y direction. So that's the reason it's called alternating direction implicit. It's still implicit. There's no iterative method anymore. So it's like, to solve for one time step, we break that into two steps. First step, you solve in the y direction, in the x direction. You have, for each line, you have a tridiagonal matrix that you have to solve. But the y values are being used for the previous time, because you have nth time that you're using here for the y values. I mean, for the theta at j minus 1 and j plus 1. And then we go in a different direction. So we sweep bottom to top, or sort of in the vertical direction, and the I plus 1 and I minus 1 values are known from the previous half time step, which is n plus half. So you only have to write, you break the one time step into two parts, and each part is done individually by solving multiple TDMAs in this case. So this is called alternating direction implicit. So to calculate its, we can actually calculate, the accuracy for this is interestingly much better. We get a delta t squared, comma delta x squared, comma delta y squared. So it's good. I mean, I would prefer this method if I wanted higher accuracy as compared to backward time center space or forward time center space, because they have order delta t in time. But this one has an order delta t squared in time. And stability, you can figure out. So what we do here is, we write the stability in two parts. So first we calculate the amplification factor, which is a n plus half upon a n, and then we calculate another one which is for the second step, which is a n plus 1 upon a n plus half, and we simply multiply the overall g is g prime times g double prime, which is the amplification factor for the whole time step. And if you do it, you will see that it comes out to be unconditionally stable. I probably might give it to you as an assignment homework problem. So it's interesting. And by the way, do visit the reading material or the reading assignments I upload. So for all this, there will be reading assignments. So the book discusses these in much more detail than what I've discussed in the class, if you'd want to explore that. Reading assignments are a part of syllabus. It's not that they're extra. Okay. This was 2 dimensions. What about 3 dimensions? How do we deal with it in 3 dimensions? So in 3 dimensions, what we do is, we break the time step into 3 parts. N plus 1 by 3, n plus 1 by 3 to n plus 2 by 3, and n plus 2 by 3 to n plus 1. In each direction, x, y and z we move. But what happens is, when you go from 2 to 3 dimensions, because realistically the world is 3 dimensional, right? Then it becomes order delta t in time, and it becomes conditionally stable. So the benefits of higher accuracy and unconditionally stability, they only work in 2 dimensions in this, with ADI. With 3D, they don't. We still go back to order delta t in time, and it becomes conditionally stable. Again, it's there in the book. Do read about it. Right, so we'll stop here now. There's a couple of other schemes to discuss that I'll discuss in the next class in the first half, and then we'll move on to the next topic of this course, which is hyperbolic equations. So we have talked about in a very good detail about parabolic and elliptic equations, and in that process we have learned a lot about schemes, we have learned a lot about iterative methods and so on. So these ideas will still stay with us. It's not that they're gone. Now we'll apply them to hyperbolic scheme in the next 1 or 2 lectures, and then the week after we'll move to Navier-Stokes equation, which will have all the terms: transient term, convective term which comes from hyperbolic, diffusive term. So elliptic, parabolic, hyperbolic, all the terms come together into one equation, and that is the most interesting thing that we'll be working with then. We'll be writing. So it becomes a bit heavy on mathematics to start with. So has everyone done a course in fluid mechanics in this class? Is there anyone who has not done a fluid mechanics course? Okay, good. So then you would understand. So if you have done it, I would urge you to please go and revisit the part where we discussed, derive the Navier-Stokes equation 1, and the second part where we talk about the terms called vorticity and stream function. I'm sure you had lectures on that. So please recall them before we start next week. We start on the fluid mechanics side. Okay, let's stop here now. Thank you.